So, Vanakkam, we will continue our lecture on engineering seismology. So, last class we have discussed about the preparation of seismotectonic map and seismic steady area identification. So, in this class we are going to talk about the seismic data, which is like earthquake data, and how to homogenization of the earthquake data. Okay, so we have seen that the identification of the seismic steady area is a very important process where you need to take a reliable seismic steady area which represents the hazard at your steady area. Okay. When you are taking a seismic steady area, you should not worry that we are taking within India border, excluding India border and all. Okay. Not for as far earthquake concerned, there is no border business. Okay. The earthquake happening in the Kashmir also affect a Pakistan. Earthquake happening in the Pakistan also affect a Indian place. Similarly, Kutch will affect a Pakistan area will affect a Kutch. So, Nepal earthquake will affect Indian side earthquake will affect a Nepal. Bangladesh also similarly. So, we should not, no need to worry about too much about any border when you talk about seismotectonic map. Okay, there is no border, only you have to worry about the geology and seismotectonic details of the particular place. Okay, not about the border. So, what are the information you collect in the seismic steady area? So, isoseismal map and intensity map decide the radius, geology data, deep geophysical, fault steady map, remote sensing and depth of earthquake, VP and VS Poisson ratio. So, these are all the information you compile and then try to generate a map as a seismic source map. Okay. So, once you generated that map, okay, the next process is compiling a seismic data in the region. Okay. So, this is also part of the seismotectonic map preparation only. So, as we have seen that the earthquake, the past earthquake location indicates how potential the area is a particular seismic activity. Okay. So, the occurrence of some earthquake in the region indicates that the seismically the area is active. Okay. So, generally seismic data are available from the National Seismic Network, okay, and then Global Seismic Network and some of the international agencies who compile different part of data and publish. So, these are all the some of the agencies where you can get a global data which includes India data also. Once you identified your seismic steady area, you have to collect a earthquake data within your seismic steady area by browsing different sources and try to collect the data and compile. So, for example, USGS, Northern California Earthquake Center, National Earthquake Information Center, IMD for Indian Geological Survey and any other site. Okay. So, it should not be limited. All the site you should visit and collect data as much as possible whatever available. Okay. So, this collection data generally consists of, okay, so the earthquake location, like latitude, longitude of the earthquake, magnitudes of the earthquake which may be in any scale ML, MD, MC, okay, MS, MB and MW any, and then the focal depth, sometimes the focal mechanism, all those information we are given. So, that is what we have seen in the last class. Okay. Some of the researchers who are described these kind of details by collecting several recorded earthquake in the region. So, those kind of informations are useful to us. Collected data will be different magnitude scale such as this one. This is the most widely represented magnitude and converted to the uniform magnitude. Okay. So, that is called as the presently used magnitude is basically a moment magnitude, okay, which is does not saturate with the any higher level. So, that magnitude has to be converted. So, now you may understand why we studied a different earthquake scale. Okay. So, in order to use an hazard analysis. So, if you understand a different earthquake scale, how it has been developed, then you believe that the moment magnitude is the most, okay, so reliable magnitude. All the magnitude should be converted to moment magnitude. So, the conversion from one scale magnitude to other magnitude is called as a homogenization. The process of conversion from one magnitude to other magnitude making a similar magnitude is a homogenization process. So, this is the some of the example where you can see that MW equal to, this is actually MW plot. So, the MB you can see ML, MB, MS. So, where you can see the saturation. So, based on this magnitude you can take what is the MW magnitude. So this is some kind of relation given with the function of seismic moment, and then MB, which is released by the Konamari using the world data in 1983. It's a very old relation. You can also see as another relation where you can see the data they used and try to compile this kind of relation. So they also given for the depth of data also they will give. So such kind of relation also developed by several people. You can see this is a typical relation developed by the Ambrasi, 1990 relation between the various, so MB versus ML, okay, so then the MB, so MS, ML and the MS. So like that there are different equations are there, and then these equations also related to the M naught. If you know the M naught, from the M naught you can get a MW. So this also you can see. You can also need to note what is the condition that equations are developed. So somebody developed equation for 6.4 to 7.8, you cannot use that equation for less than 6.4. So those are all the clear understanding of the equation and use. Because somebody used, you should not assume that equation is right and you should use, including myself. If I publish some paper using some equation, you should not assume that equation is right. You have to verify yourself how that equation is applicable to your region. Okay. We will also see some of the most widely used equations. So this is actually the equation given by the Scott List. So this was actually considering the global data where he considered 20,407 earthquake. So this is the distribution of the earthquake, you can see where he plotted. But you can also note here that India has a very small number of data, you can see here. Okay, so where you can see this is actually the India, you have very small number of data here. So you can, he has given MS versus MW. Okay, so MS versus then the another MS, MW. So this he proposed this kind of equation and range of equation is here. So these are all the some of the equation. You should need to know these equations, but again I am telling that I am not recommending any particular equation to be used. You have to select this equation according to the your region, okay, not based on the literature or known data. So the earthquake magnitude conversion, so the Timbajam also given some equation. This is basically for the Indian data, you can see here. Okay. So this is from the Indian earthquake, he has converted, and this was published in 2004. So where they given MS versus MW, MB versus MW relation. So then the Srivalsa et al. 2011, he also published some equation. So using the Indian data, you can see here. So these equations you can see. So they are given like that. So even the other after that Ashish et al. 2016, so he published some equation, you can see here. Okay, so this is all considering the overall Indian data. So when you consider overall Indian data, you should also know that okay, we have different seismotectonic behavior at different part of the India. So that you have to account and wisely take which equations are more suitable. Okay, so they also given like the different conversion, okay, from this to that and that to this, so something like that, so that you can do conversion vice versa and get finally a moment magnitude. So this is another equation published by the Nath. So where he compiled, okay, 2017 they compiled data from the different reliable website source, and then the IMD and then the previous studies, and then the nomenclature all this the magnitude scale which is reported in the region and their saturation. Okay, so the saturation level, and then so the source of that saturation level, from here they went to the developing a magnitude conversion equation. So which is like the equation which is given here, you can see here. Okay, this is the equation for the typical conversion. So they used two different set of data and number of data. So they mention like the minimum magnitude, maximum magnitude, converted magnitude range. Okay, so the equation number for the paper reference actually. You can see the equation range. Okay, so which earthquake should be, what conversion you should use, all these things you should know. So you can see that the highest range given was here actually a 7.6, 7.8 actually. Okay, so that means, so if you have some other earthquake which is beyond this, one has to be really concerned about those kind of things. So you should know in detail before using any kind of relation which is useful or not. They also taken here basically the praxi magnitude concept, where they take this by considering the praxi of this point, by applying a proxy magnitude concept for getting the better regression model. Okay, so to get a better regression model, again what type of regression model they use, that is also plays a major role in the your conversion equation. So so this is the earthquake after conversion and declustering. So these people published a map, okay, seismic map from 1900 to 2004. Okay, you can see here. So the legends used. So in almost southern India, okay, so the entire part of southern India, okay, this is the peninsular India kind of things. So your highest magnitude reported is basically only 6.5. Okay, so there is no beyond that magnitude. So red dot is exactly 6.75, that you can see mostly on the this part. Okay. So here also you can see some of the area this is not there, but that is a plate boundary. So that those kind of places also you should put some kind of effort and try to see, okay, so there is any kind of seismic activity is happening and to fulfill the seismic gap kind of things. Okay, so that kind of so this paper details are given here. So this is a figure taken from that paper actually. Okay, so then actually if you see this equation, most of the equation concentrated on the throughout India. So in order to understand, okay, how the seismic magnitude conversion will affect your seismic hazard analysis results, we carried out a study, okay, considering the northeast region as our study area. Basically we have taken a northeast as a seismic study area and tried to get a seismic study area map based on the intensity and collected a different earthquake and tried to generate our own regression model and then try to take a previous models and try to assess how this model conversion will affect your number of data. Okay, so then how the AB parameters will be affect. AB parameter will be discussing in the coming classes, and then how it affects really your hazard values. So that is all we studied by taking this paper. If you want to know more about that, you can see. So we used actually least square regression as well as orthogonal regression. Even we studied the effect of regression model, okay, on the conversion equation and that effect in the hazard. Okay, by looking at this study, this paper was published last year actually, about 1 year back. So this is the general functional form we used for the model, and this is the equation we have given. You can see MB to MW, ML to MW, MS to ML, MS to, you can see the number of data points, R square value of that, and then the magnitude range which is applicable. Okay. So this paper further, I am only presenting this equation. Further we carried out study and concluded, okay, what are the important observation we should follow when you do the conversion equation. So you can refer those kind of things in the from that paper. So once you convert and homogeneous data, so now since you have collected data from the different source, you will have the same earthquake from the reported on the different source. Okay. So that means there will be a main shock and repeated main shock, okay, and then the aftershock and foreshock. So generally, okay, the aftershock or foreshock doesn't contribute to the seismic activity of the region. Why? Because it is a minor earthquakes, okay, generally minor earthquake which will be smaller in size and energy release also smaller. The main event only we should be focusing on the concentration. So the phenomena of earthquake is modeled as a Poisson distribution. The earthquake occurs randomly with no memory of time and size and location. So that means there should not be any overlap of earthquake, same earthquake in the region. That has to be taken care. So all the foreshock and aftershock has to be removed, okay, from performing the any seismic hazard analysis. Before doing seismic hazard analysis, you need to remove the foreshock and aftershock. In order to forecast a correct seismicity due to the future earthquake, the removal of dependent event, okay, the foreshock and main shock and repeated main shock mandatory, else it will lead to the highly conservative result and increased seismicity. Okay. So the Risenberg proposed a static window test which states that all the event occurring within the 30 kilometer distance within the 30 days period are considered related to the on event and foreshock and aftershock. So you should remove the event within this band. Again I am telling that this was suggested by the Risenberg. So recently we are doing research on that to understand how the declustering window should be defined for Indian data. Okay, so maybe we will come up with the result, you can refer in the future. So the removal of, okay, so the dependent event from the main shock is actually a declustering process. So why the declustering? For example, so the phase and time, if you look at earthquake, so this is the overall earthquake what you collected and converted, but the main events are only the red one, remaining all after shock and foreshock are repeated event. So this will contribute to, this is actually the total data frequency time relation. So this is the data only for the main shock. So it will show a increased seismicity. So in order to avoid that, you should do the declustering process after conversion. So once you decluster the data, then the remaining data you can plot on the source map earlier you prepared, and now you have a seismotectonic map which consists of the seismotectonic parameters and the seismic data. So that map is called as a complete seismotectonic map ready for hazard analysis. So this is the seismotectonic map, this is the steady area Bangalore, seismic steady area. You can see the scale of the map, and then the legend is given, and then different scale, and then the source details, all the information has to be prepared. Here this is the typical seismotectonic map prepared by me for the Bangalore microzonation work. Okay, so we have done systematically, selected a steady area, collected a seismotectonic parameters, geology parameter, geophysical parameter, collected a data, converted that and declustered, homogenized and declustered, and finally superimposed all the data and prepared a seismotectonic map. So now you will know that what are the source associated with the earthquake, what are the places there is no source but still there is a earthquake. This has to be modeled well for further analysis. Okay, so that discussion we are going to continue in the next class, okay, as the this one. Okay, so this analysis, okay, so whatever going to do that. So the first part after declustering, the first part is you have to understand your data is complete or incomplete. So what is mean by complete? So complete means the your region, okay, the complete means you should have all the range of recorded, okay, in the particular place, that is called as a complete data. So for example, last 10 years I have, after installing the seismometer, I will have minor earthquake to major earthquake recorded everything. So that details is the complete period. Okay, but when I talk about 100 years, my instrumentation started very late, I may not have the minor earthquake, only the earthquake which is felt by the people, okay, like isosysmal map. So that period is called as a incomplete period. Or you can say that the earthquake complete, okay, and incomplete with depends upon the analyzing systematically, and the complete data follow some pattern with the time. Okay, so that kind of analysis called as a earthquake data completeness analysis. So with this analysis basically proposed by the STEP, okay, 1972, he has given a method, okay, to describe and analysis the completeness of the earthquake data. So what he said actually, so the whole data, okay, need to be divided as a number of occurred suitable time interval bins. Okay, so like every 10 years, 5 years you can make a bin. Then you can count each bin, okay, what the number of event or particular magnitude range. Okay, like 4.5 to 5.5, how many earthquake, 5.5 to 6.5, how many. So like that each bin you can estimate. So when the sample set more, the variance will be small. That means you should divide a time period and a number of data should be smaller as possible. So if the x1, x2, x3, xn is the number of event unit time interval, then the unbiased mean of each time interval of data set can be given as a lambda is equal to 1 by n into, okay, so the epsilon I equal to 1 into n into xi. So this is the rule it has been followed. So corresponding standard deviation, okay, the sigma lambda square is equal to lambda by n, when n is the number of unit interval, keeping the time interval of 1 year, the standard deviation proportional to the sample data. So this is the T you will get. So that means for the stationary process, the variance of unity standard deviation will be proportional to 1 by root 2. So if the data follows a pattern of 1 by root 2, that data is complete data. Data which doesn't follow a pattern of root 2, that data is incomplete data. So this will give you the complete period, okay, the earthquake data complete period in the this one. So you can see that the typical data we have taken. Okay, so then the time interval we made, and then the standard deviation we prepared, and data has been divided as a different segment. You can see the symbol. So this line actually, this red line is actually 1 by root t. So that you are copied along, you first plot your data and copy these lines parallel to that, then identify which are the data are following the line. So the data which follows a line is a completeness period. So generally the instrumented data will be complete for the short period, larger magnitude data will be complete for the longer period, because that has been felt by the people, definitely it has been reported. So this is actually the time of completeness as period of completeness. So the another one is actually the magnitude of completeness. So the magnitude of completeness means what lowest magnitude the data is recorded, okay, in the region. So that what you can do a cumulative number of and magnitude versus a plot, and is wherever you see that there is a slope starting, okay, that point is actually considered as a magnitude of completeness. So you can get a period of completeness and magnitude of completeness. So which will decide what is the lowest magnitude you have the accurate data and what period in your region. So that is what you will get from the completeness analysis. So this completeness analysis, okay, also a part of your seismic hazard analysis, where you get a period of complete and a magnitude of complete. Okay. So the seismic data, what we have seen that you have to collect your data, homogenize and declustered, and then superimpose on the seismotectonic map and get a seismotectonic map. Okay. After getting that, you will get a minimum maximum earthquake data in the region, seismicity mapping distribution of the earthquake data, which will help basically to get maximum earthquake in the region and recurrence model for the region. So this is the both application which we will be discussing in the next class. Okay. So thank you very much for watching this video. We will meet in the next class and talk about the how we can estimate maximum magnitude based on the seismotectonic map and the seismicity details collected in the literature. Okay, whatever we compiled. Okay, and also followed by the recurrence model in the coming classes. Thank you very much.